All right, you're in Exploiting Lawful Intercept to Wiretap the Internet with Tom Cross. Tom is the X-Force Manager, X-Force Research Manager, sorry about that, at IBM. Tom?
Thank you. And thanks everyone for coming to hear my talk this morning. Can everyone hear me okay?
A little low.
Little low? Let me move this up. How's that? Better? Better. Okay. So, where do I start? All right. So I'm here to talk about lawful intercept systems in the internet and security issues with them. So a lawful intercept is a wiretap. It's a lawfully authorized wiretap. And there's been this debate that's been going on for I would say as much as 30 years now about how the telecommunications infrastructure of the future will work regarding the ability for law enforcement to perform surveillance of suspected criminals. And the debate is sort of defined by this belief that this sort of surveillance is either going to be easy or you're either going to have end-to-end encryption and there's really not going to be a way to do any surveillance, or we're actually going to be building infrastructure into the internet that enables surveillance. And so if we're going to, and so there's been all these different sort of salvos in this debate. One of the first was the Clipper chip, and you heard about it from Moxie earlier if you were in this talk. He kind of teed up a couple of the topics that I'm going to discuss. So the Clipper chip was an encryption system that had a backdoor, so the government, if lawfully authorized, could listen to your communications. And one of the things that happened to the Clipper chip is, in fact, the crypto system was proven to be weak. And so, as a consequence, someone might be able to access the data without authorization. There's, at about the same time, this is from the early 1990s, in the United States, this law called the Communications Assistance for what? Okay, we're going to switch. Okay, can you hear me now? It sounds louder. All right, so there was this, in the United States, there was this Communications Assistance for Law Enforcement Act, and what it said is that if you were building telecommunications infrastructure, you had to create facilities that allowed law enforcement to access the content on your network. The impetus for this was that at that time, telecommunication systems were getting more and more complicated, and so the idea of simply wiretapping by using alligator clips was becoming outmoded, and they knew that that was going to continue to happen in the future. So they wanted to sort of require the phone companies to build in a way for them to do this. CALEA has parallels in other places in the world, and that's going to be important as I go through this discussion. In 2005, the FCC ruled that CALEA applies to broadband internet providers. So originally, when CALEA was passed, there was this compromise that said that internet services were not covered. But over time, they, I don't know, it's somewhat of a reversal. It's not a complete reversal, but they decided that broadband internet providers were telecommunications companies, and so they had to comply with CALEA. So that brings us, so originally a lot of the CALEA equipment had to do with wiretapping telephones, but if we have to comply with CALEA in the internet, then we need to have internet wiretapping infrastructure, and that's how we get to this discussion. The IETF published an RFC, which was RFC 2804. I think it was in the year 2000. About the concept of internet wiretapping infrastructure and whether IETF standards should take internet wiretapping into account. And their argument was that they should not, and there's a bunch of different reasons for that. But one of the arguments relates to that thing that I said before, that sort of bifurcation in this debate where you think that wiretapping is either going to be easy or it's going to be impossible. You're either going to have end-to-end encryption where you can't do any wiretapping, or you're not going to have you're not going to have enough encryption, and so there's going to be a place where it's easy to hook up and do wiretapping, and so you don't need infrastructure to support that. The other thing that the IETF said is that the internet should be free from security loopholes, and there's a concern that if they build wiretapping capabilities into the internet, that they could represent a security weakness that could be exploited by somebody. So in having said all of this, the IETF also said that if you're going to do this, if you're going to build an internet wiretapping infrastructure, that you should publish the details of your architecture so that people can peer review it from a security perspective. And this makes a lot of sense if you consider the fact that all of the protocols that underlie the internet are all public documents. They're all IETF RFCs that you can go download and read. Anyone can understand how the internet works. And so if there was some secret mechanism that was being used for wiretapping in the internet that wasn't also subject to being published in this way, that would sort of be antithetical to the overall overarching philosophy upon which the internet was built. So in keeping with this policy, Cisco published an RFC 3924, explaining their architecture for lawful intercept and IP networks. Cisco had to create this architecture because they have customers who are forced to comply with CALIA and other similar laws in other countries, and so they have to introduce wiretapping infrastructure into their internet systems. And so Cisco came up with an approach, and they published it in this RFC. And basically, so their approach is loosely based on an architecture which was defined by the European Telecommunications Standards Institute for wiretapping. It's an SNMP v3 based interface that allows you to, there's a MIB that you can access that allows you to provision a wiretap. So one of the reasons that the IETF said that you should publish these architectures is so that we can peer review them for security reasons. And so that's what essentially I'm going to do in this talk. I'm going to look at this architecture and consider some of its security properties. And I think that there are properties of this architecture that are not as secure as I think they should be. And so I have some input about how I would design this if you ask me. So the first thing I'm going to do is I'm going to explain how this architecture works. So here's the overall architectural diagram, which I pasted right in from the RFC. The thing over on the right that says LEA, that is the law enforcement agency. So some of these blocks in this diagram are actual network devices, and some of these blocks are groups of people. The LEA is a group of people. They decide that they're going to perform a wiretap. They go out and they get lawful authorization to do it, and they go to this thing called the LI administration function. That LI administration function is also a group of people. They usually work for the service provider, or the service provider can outsource this to a third party. These are a bunch of sort of screenshots of advertising material for different companies that offer this lawful intercept outsourcing service. And so what these guys will do is they'll take the authorization. They have lawyers there. They'll take the authorization from the law enforcement agency. They'll validate that it is in fact lawful, and then they'll go and they'll provision the wiretap that was specified in the warrant or whatever authorization these guys had. They provision the wiretap using this thing called a mediation device. And the mediation device is in the center of this diagram, and as you can see, it's sort of the architectural core of this lawful intercept system. The mediation device goes out and sends messages such as this SNMP v3 message to devices that can actually do the wiretapping, and then it collects the results of that wiretap and packages it and provides it to the law enforcement agency. There are a bunch of different companies that make mediation devices that interoperate with Cisco routers and support the Cisco architecture for lawful intercept. And this picture is just it's from the marketing material from Verint, which is one of the companies that makes these mediation devices. So there are two IAPs in this diagram. An IAP is an intercept access point. There's two kinds of them, and this represents sort of a historical concept in most Western legal systems that there's a difference between collecting content and collecting addressing information. The most ancient kind of telecommunications is a letter, and a letter has an envelope with an address on the outside, and so a postman could easily see who you're mailing letters to, but in order to read the content, he'd have to go to the trouble of steaming the envelope open in order to read it. And so most legal systems over a long period of time have developed this idea that in order for the police to see addressing information, who you're calling, who you're emailing, there's a sort of a light amount of lawful authorization that they need. They don't have to have a high level of suspicion. They don't have to have a lot of documentation. But there is some process that they have to go through, but it's not as heavyweight as the process that they have to go through if they actually want to see the content. The content is more carefully protected. And so that actually ends up being reflected in this technical architecture. There are two kinds of intercept access points. The IRI intercept access point can only collect, it's a specific device designed only to collect header information or routing information for cases where these guys only have the lawful authority to collect that kind of data. The content IAP it can collect the entire content of someone's communication. All Cisco routers who support this interface are content IAPs. So I'm not going to talk about IRI IAPs anymore in this talk. So there's this interception request, labeled D here, that is the SNMP v3 request that I talked about before, that gets sent by the mediation device to the router and tells the router to go ahead and provision a wiretap. The interception, so this is sort of part of the MIB for the interception request. The MIB is published in an internet draft. It's not an RFC, but you can find it fairly easily by Googling around. There's a bunch of different things that the person provisioning the wiretap can specify. They can select the source and destination addresses and source and destination ports for the traffic that they want to collect in their wiretap. And they can also specify where they want that data to go once it's been collected. They can specify the address and port number of the destination host, what transport, and I'll talk in more detail about that, and whether or not notification is enabled. So there's a lot of flexibility in this architecture. So let's take a step back from this whole thing and ask ourselves, like, what are the different security issues you would need to think about if you were building this wiretapping system? The first thing you would want to do is prevent the subject from discovering the surveillance. In the RFC that Cisco published, they describe the fact that they don't add additional hops to a trace route, for example, to make it obvious that there's a new device in the network. They built it into the router that's already there. Some people have asked, whether enabling this interface would have a performance impact in the router, and I wasn't able to study that, but it's an interesting question. If you could observe that the network performance is slow today, that might mean that they're wiretapping, but it could mean something else too. So I don't know how reliable that would be as a method of detecting the presence of this. Another thing that you need to think about if you're designing a wiretapping system is preventing the subject from manipulating the surveillance. So there's a really interesting paper called The Eavesdropper's Dilemma that Matt Blaze wrote and published, I think, a couple years ago that talks about this subject. If you suspect that you're being wiretapped, so let me explain it from the other perspective. If you're wiretapping somebody, and if you they send a packet, for example, with a bad checksum, you can do one of two things with it. You can either throw it out because you think that the end host is also gonna throw it out, or you can include it with the content that you've collected because you think that the end host might actually interpret it. And so that gives the subject a couple of different options if they want to confuse you. If you're collecting packets with bad checksums, they can send a whole bunch of those in addition to the real messages that they're sending. And those additional messages that they're transmitting that aren't being received by the receiver might confuse the person performing the surveillance as to what's being discussed. On the other hand, if you decide you're going to throw out packets with a bad checksum, then the guy who's being surveilled need only configure the computer on the other end to accept packets with bad checksums, and he can send all of his communications with bad checksums, and he'll be completely invisible to your surveillance. So that's a difficult problem, and there's a lot of other research out there that discusses it. The other thing that you need to be concerned with is unauthorized use of the wiretapping system you're building, and that's really what this talk is about. You need to prevent people who don't have permission from provisioning wiretaps, and you also need to make sure that those who do have permission are only collecting the information that they're authorized to collect. That second thing, there's a technical term for it, which is minimization. And those two things are really the subject of this talk, and I want to make sure that's clear because in the last time I gave this, some people didn't understand that. This talk is about gaining unauthorized access. This is Blackhat. So this is a network map to try to give you more of a real-world picture of how this is going to look. This is an ISP network. There's an edge router down here that's providing service to a bunch of customers. It's an intercept access point. And then there's the service provider management network that hopefully is firewalled off from the rest of the ISP's network. And in it, you've got a bunch of computers, including an SNMP management host and a mediation device that you're using to operate the surveillance system. So this is how things are supposed to work. The mediation device would send this SNMP v3 interception request through the network to the edge router and provision a wiretap. And then a wiretap would flow back across that red link there from the router to the mediation device, which would collect it and send it off to the law enforcement agency. This is an idealistic attack scenario. Some guy out on the internet sends an interception request to that same router, provisions a wiretap, and has the results of that wiretap sent back to his machine, again, out on the internet. So how do we do that? What we're going to need to do is send an unauthorized interception request. It's a single, properly authenticated SNMP v3 packet, which accesses this tap MIB, which, as I told you before, is available online. You need to know the correct username and password for the interface. You also have to know the SNMP v3 engine ID, engine boots, and engine time values. Those values are designed to prevent replay of SNMP v3 transactions, and they are readily available from the router if you're allowed to transact SNMP with it. So it will tell anyone what those values are because they're not supposed to be secret, and you can share them between hosts. So if you know them, you can tell someone else and they can use them. The attacker would also need to be able to, the attacker would need to be able to send a packet the interface will receive. So packet filtering could impact this, but again, it's a single UDP packet, so you could spoof it. And I'm going to talk a little bit about that. And encryption might prove to be an obstacle, but only if they did it right, and they probably didn't. So I'm going to talk about that too. Let's start with the beginning. Let's talk about this correct username and password business. It actually turns out that you don't need the correct, or for unpatched routers, you didn't need the correct password because of a vulnerability in the SNMP v3 implementation that this actually affected a whole bunch of different vendors, and not just Cisco, but it was disclosed in the summer of 2008. So the way that SNMP v3 messages are authenticated with this message digest, and so you, as the client, you calculate the digest, you attach it to the packet, you send the packet to the server. What the server is supposed to do is to see how long the message digest you sent was. And if it's not 12 bytes long, it's supposed to throw the packet out. It pretty much says that in black and white in the RFC. But a bunch of people didn't implement that step. And so they set the packet onto so the next thing they do is the server does is calculate its own HMAC for the packet. And then it wants to compare its HMAC with the HMAC that you sent. And a lot of these comparison operations were implemented as shown. They take the packet's HMAC buffer and their HMAC buffer, and they compare using the length of data that was in the packet. So the consequence of that is that if you send a single byte, as long as that one byte is the same as the first byte of the valid HMAC for the packet, your packet is accepted as valid. And so really what you do is you send 256 of these things, one for each possible byte, and one of them will be accepted. Or the other way you can do this, and it gets more complicated, is that the valid HMAC changes constantly because of the engine time. So you can actually send the same byte over and over and over again, and one of your packets will be accepted. As I said, this was disclosed in June 2008. I hope everyone has patched this, but people tend to be slow about patching routers. So you've got to take the router down. The new version of iOS might have a bunch of new software features that you want to test on your network, and so it can be complicated to deal with this. So I hope that everyone is patched by now, but there might still be routers out there that aren't patched. What's also interesting is that most of the versions of iOS that support this lawful intercept technology were not vulnerable to this particular vulnerability. And given that this vulnerability existed in implementations for like 6 years, it's surprising to me. There must have been 2 different SNMP implementations floating around in their code bases, and one of them didn't happen to have this flaw. But I did find a specific version. There may be more, but I did find a specific version in the list of vulnerable versions that happens to also support lawful intercept, and it runs on the Cisco 10000 series edge routers. These routers are for cable modem companies or DSL companies that are serving like large numbers of customers. These things are out there on the internet, and potentially there's a lot of consumer data that's flowing through them. So let's say you're trying to break into this lawful intercept system, and these guys have patched the router. So that vulnerability is not available anymore. You're going to need to actually have the valid username and password in order to get in. You're going to have to brute force them. Turns out SNMP v3 makes that really easy for you, but through a very classic mistake. They have very verbose error messages. If you send a packet to an SNMP v3 interface and you have the wrong username, it will tell you that the username was wrong. If you have the wrong password, it will tell you that the password was wrong. And so it's easy to guess usernames until you get one that's accepted, and then you guess passwords until you get one that was accepted. And that helps break up the amount of entropy that you need to guess without getting any feedback. All kinds of different systems have been implemented this way in the past, and usually this ends up getting disclosed as a vulnerability with a very low CVSS score, and they fix it. But it's actually going to be hard to fix SNMP, and I'm going to talk about that a little bit later. So let's say you've brute forced the username and password. You might be a little bit concerned, because it's going to take you a while to try all those guesses, that you might be noticed doing that, right? All that traffic that you're generating, you would think that might be picked up by the people operating the network. But unfortunately, there really isn't much of an audit trail in place that would alert the network managers to this activity. So I originally thought that this was an implementation flaw. In SNMP v2, if you send a message to, so they didn't have usernames and passwords in SNMP v2. They had community strings, which was sort of like a password. But if you sent an SNMP v2 message to a router that was configured to do traps, and you had a bad community string, it would do this authentication failure trap to the SNMP management server. So the network managers would know that somebody's screwing around. Somebody is sending us messages that are not properly authenticated. And all the documentation seemed to strongly suggest that if you configured SNMP v3 with either notification traps or informs, is what they're called in v3, that they would be generated if a bad username and password were sent. But it turns out that that doesn't actually happen in practice. I tested this on a bunch of different iOSs, and no traps or informs were generated when bad passwords or usernames were tried. So I told Cisco this, and they spent some time thinking about it, and they decided that the behavior was as designed, and the documentation was wrong. And so they actually have this bulletin in CCO, which you can look up, which explains that the documentation seems to imply that we will generate traps when there's an authentication failure, but in fact we do not, and it's supposed to be that way. So you can try bad usernames and passwords all day long, and no one will probably notice. The other thing is that once you get in, you would think you would be noticed. Once you crack the right username and password and you actually provision a wiretap, you would think there would be an audit trail that would be generated, and they would know that the wiretapping system was being used. It turns out that you can actually turn the logs off. In the MIB for provisioning a wiretap, the tap MIB, there's this notification enable value, and you can set it to false. And if you set it to false, no traps or informs will be generated denoting that a wiretap took place. This is also as designed, and to me it's bizarre. Most kinds of systems have audit trails built into them and various levels of authorization. So if you're logged into a Unix shell, you're generating all the syslog activity, and you can't turn that off unless you're root. Right? DHCP servers have audit trails. SMTP servers have audit trails. Every kind of computer system that we have audits the activity that the users are engaged in. But this is different. In this case, the user can turn the logs off. And it seems that a bunch of different lawful intercept technology that is completely unrelated technically has this same architectural feature. So there was this article in IEEE Spectrum back in July of 2007, which is very interesting, which involved some Ericsson cellular phone switches that were in Greece. And I want to make it clear, no Cisco equipment was involved here. These were totally different machines built by a different company for use in the cellular network with a completely different technical architecture, except that they had this same flaw, that there was a disconnect between the device that performs the wiretapping and the actual device that, or the device that's used to provision the wiretaps. And the logs were all kept on the provisioning device and not on the device where the actual wiretaps occurred. And so what happened is that someone got a rootkit installed on the actual cellular phone switch, and that rootkit accessed this interface for wiretapping, and it could do so without generating any audit trail because the audit trails were all over here on the provisioning device, which it never touched. Ericsson discovered this because there were some problems with the switch. It started crashing, and they sent some escalation engineers down to Greece to find out what was going on, and they started looking through the core dumps, and they actually found assembly code in the core dumps that their company didn't write. It's like the support escalation nightmare of all time, right? You find this assembly code, your company didn't produce it, and it turns out it's spying on people. There's an origin to this architectural flaw, and I don't know exactly what it is. And I'll talk to you about that a little bit later. But there's some reason why all these systems have been designed this way, and I don't know exactly why. But I think it's a problem, and I have a suggestion for an alternate architecture. So there's one other reason why this is a problem, even if you decide that you're not concerned about unauthorized use, and that is that allegations of misuse of the system cannot be investigated. If somebody says, I was wiretapped without authorization, you have no way to go back and see whether or not they're lying. And so that's an interesting problem in and of itself, I think. So you can crack the password, or you can exploit that vulnerability to get in. There's no logs that are being generated of your activity. What about the output stream? You would think that the output stream would only go to the mediation device. And so that would be kind of a problem because you would need to own the mediation device, and it's probably pretty secure. But it turns out that you can send the output stream anywhere that you want. You can send it to any destination address on the global internet over any port using one of 4 different encapsulation methods, a UDP, 2 different UDP formats, one of which is based on RTP, a TCP, and an STCP stream. So it's very unlikely that your output stream is going to be packet filtered or even noticed. And so, for example, you could send all of your wiretap out over port 53 as a bunch of UDP packets. And I put a picture of Dan Kaminsky up here because every time I think about port 53, I think about Dan. So it's very unlikely that your wiretapping contents are going to be discovered flowing across the network, and you can pretty much send them anywhere you want once you've got this packet accepted. So usually people who are configuring routers will use access lists to protect them. That is the primary security feature of iOS. All of the documentation for either both the SNMP v3 authentication vulnerability I mentioned before, as well as the hardening guides, suggest that you create these infrastructure access control lists, where you basically say the service provider LAN is the only place that will accept SNMP packets from. Now, the problem is you can spoof this interception request, so you don't actually have to have access to that network in order to use this feature. But in practice, you probably want to. As I mentioned before, you need these engine values. They can technically be guessed, but I'm stretching the word technically there. It's very difficult to guess them in practice. So you're probably going to want to ask the router for them. And in order to do that, you need to be coming from an address that the router will interact with. If you want to use those error messages to crack the username and password, you need to receive them. So again, you need to be in an address that the router will interact with for SNMP. So these infrastructure access control lists do have a practical effect on the viability of this attack, even though in theory you could bypass them through spoofing. So this network map kind of represents what I think is a real world attack scenario. You've owned a machine in the service LAN. It could be any machine in the service LAN. And then you send your interception request from that machine to the edge router, and then the edge router sends the wiretap to your computer out on the internet. So immediately you get this reaction, well, people either say, oh, the service lands are impenetrable, so that's not a problem. Or they say, well, once you're in the service lane, you pretty much control the ISP anyway, so what difference does it make? There are two differences. The first is that there are a lot of people who have legitimate access to the service LAN who are not supposed to be using lawful intercept. And so the security architecture here is actually supposed to provide better assurances than this, and it doesn't. So that in and of itself is an issue. The second thing is that we've built all this awesome functionality that makes it really easy to perform wiretaps. And so that makes controlling the service LAN suddenly more attractive than maybe it otherwise would be. There's a FRAC article from I don't know, 10 years ago that talks about how to, if you control iOS, you can configure essentially the same sort of wiretap where you set up a tunnel, an IP tunnel from the router to some device out on the internet, and you route a particular traffic set through this tunnel, then back, and then out. And so you can set up something like that. It's extremely cumbersome. The person that you're targeting might notice it. This is a single UDP packet. It's a hell of a lot easier to use. And so the fact that it's easier to use makes it less expensive to perform this attack, essentially, and so it becomes more attractive. So I work in X-Force research. We make intrusion prevention systems, and we spend a lot of time looking at security vulnerabilities and trying to think about which security vulnerabilities are more likely to get exploited than other ones. And we came up with this sort of simple way of talking about the process that we go through, where we consider the economic prospect that a vulnerability represents to an attacker. And so I've got this chart here, and on one axis, I chart the opportunity that a vulnerability represents, like how many systems out there are affected, and what kind of data do they have on them. On the other axis, I chart how much it costs the bad guy to exploit that vulnerability. Does the vulnerability fit into a business model that attackers are already running, or are they going to have to come up with a bunch of new tools and techniques in order to really exploit it and make money with it? So if you think about this, the fact that we've created this infrastructure that makes it really easy to do this, what you end up doing is moving this attack to the right side of this chart. Basically, you're making it less and less expensive to perform the attack, and the consequence is that it becomes more attractive. Most of the vulnerabilities that X-Force gets really spun up about are the ones in this top quadrant that represent a big opportunity and are real cheap to exploit. Anything that you do that makes things cheaper makes them more likely to happen in practice. There's another kind of access list besides these infrastructure access control lists that you can configure on a Cisco router. And it turns out that it has a big impact on the security implications of this interface. But unfortunately, it's not, at least originally when I looked at this, it was not documented in the SNMP v3 hardening guide or the configuration guides for lawful intercept. So I'm pretty sure no one actually does this. But you should if you actually have to deploy this stuff in practice. You can specify an access control list for an SNMP v3 user. So that user can only come from a specific source address. And again, the interception request could be spoofed. So in and of itself, this does not solve all your security problems, but coupled with other things, it can. It may be difficult for an attacker to figure out the IP address of your mediation device. And the other thing is that this actually generates an audit trail. Once you configure this access control list, if you send a packet to the router using that username from a different source address, an authentication failure trap will be generated. So that's a strange result in my mind, but it can help you identify when things that are suspicious are going on. So this is a good thing to use, but I don't know if a lot of people are actually using it. Another good thing to use is encryption. And I know for a fact that a lot of people are not using encryption with this system. You don't have to have encryption to have the lawful intercept feature. And the documentation says, although encryption is not necessary, we recommend it. And I know that they do. Cisco really wants you to use encryption with this, but sometimes you can't afford the encryption version of iOS on your router. And so there's a couple different kinds of encryption that you can use in this context. One is SNMP v3 encryption, and it's a good thing to use because it makes the attack a little bit harder, but it doesn't protect the privacy of the wiretap coming back out. And so what a lot of people do if they're using encryption is they set up an IPsec tunnel from the mediation device to the router. And that's actually mentioned in the internet draft for the Part.mov. That's how they meant you to do this. But the problem is, again, that IPsec tunnels are disconnected from the actual lawful intercept or the SNMP v3 system. So imagine that there's an IPsec tunnel configured in this case between the mediation device and the edge router. I'm sending my attack from a different source. So when the router receives my attack packet, it's not going to expect it to be encrypted. So the fact that your tunnel is there does not prevent me from accessing the interface without authorization. When my output stream goes out, it's not going to the mediation device. It's going to a different destination on the internet. So again, the IPsec tunnel is only going to encrypt traffic if it's headed for the mediation device, and my output traffic is not. Even if you did go to the trouble of configuring IPsec, it may not necessarily protect you from this attack. Only if you couple IPsec with that user group access list that I mentioned before are you really secure against unauthorized use of this interface. And I don't think a lot of people are doing that in practice. So this is one of the questions. It's like, what do I think people are doing in the real world? I think they're using that infrastructure access control list, and hopefully some people are probably still vulnerable to that authentication vulnerability. Some people are not using encryption, and most people are not using that group access control list. So the consequence is that these systems can be attacked in the real world, and that this attack scenario is realistic in a lot of places. So let me shift gears here and talk about what should be done to address these problems. So there are different layers at which you can address security issues in an internet protocol. You can change the design, you can fix the implementation, or you can just deploy it right. I have some recommendations for proper deployment. I'm not going to bore you with them. As I said before, you can configure this in such a way that it is pretty secure against this attack. I just don't think that a lot of people do that in practice. But there's a couple problems with this. The first is that even if you do this, even if you configure it securely, you still don't have an audit trail. So you still can't investigate misuse of the system by people who are authorized to use it. There's also no way for me as a user to know whether or not my ISP has deployed this correctly. And again, I assume that a lot of ISPs have not. So if you made changes to the design of the protocols, it would make the system harder to attack regardless of how well it was deployed. I have a bunch of recommendations for that. For SNMP v3, I think that we should get rid of those helpful authentication errors that tell you whether the username or the password was bad. We should send traps and informs with any authentication failure occurs, so the network managers will know when someone's trying to crack passwords. We should also make the engine values more difficult to predict and share. So I would love to be able to do these things, but unfortunately, the working group for SNMP is closed. So the process of actually getting the IETF to update the standard to include these changes is this Byzantine bureaucratic discussion that would take several years. So it's not going to happen. These things are all really easy to implement in practice. If you did this to your SNMP implementation, you wouldn't have to have a flag day or anything. You could just deploy it and it would be fine. But unfortunately, that's not going to happen. I also have some recommendations for lawful intercept. The most important one is that notification control should be moved into the router configuration so that there's an audit trail for every single wiretap that takes place. Now, one of the reasons for the architecture that exists here, where the audit trail is in the mediation device and not in the router, is that they don't want the people that run the network to know when the police are wiretapping somebody, because they're not necessarily authorized to know that. So if they could go in the router and configure any destination to receive traps whenever the wiretapping system is used, they would know when wiretaps are taking place, and they could call their friend and say, hey, they're wiretapping again. That's why they wanted the lawful intercept administration people to control the notification so that the router administrators wouldn't be able to find out what was going on. So what I suggest is you actually need to have agreement between the people who are operating the wiretaps and the people who are operating the network. So when you configure the router, you can configure a bunch of different possible destination addresses for traps. And you enforce that when a wiretap is provisioned, they must specify one of those different destination addresses. If they don't, then no wiretap happens. And this allows you to have different law enforcement organizations that have different security policies using the same infrastructure and the reporting And they can all control their own reporting so that each one doesn't find out about the other's activities. Again, I don't think that change is going to happen. This design, as it exists, complies with government requirements. And I put that in quotation marks because I don't know which government and I don't know what requirement. Someone mentioned the ETSI standards to me, and I went through the ETSI standards and tried to find a place where they require that you have a way to turn the audit trail off, and I didn't find it. So I don't think it's in there. I don't know where it is, but we see it, again, in totally different lawful intercept systems designed by different people in very different ways. And so there's some fundamental origin of this decision. But the other thing is that network providers are not demanding it. So I want to talk about this. I want to talk about this issue a little bit more, the design, implementation, and deployment. With IETF protocols, you have these protocol designers that design an RFC standard, and then you have these software vendors that actually implement it, right? They make the software that implements the RFC. And then you have these network operators that take that software and they actually run it on the network so you can use it. And then you have customers who actually use that system. In this case, the customer is law enforcement. They're the people who actually access this lawful intercept system, and they're the people who are setting the requirements for how it should work. You're not the customer. What this is, so in economics, this is called a negative externality. And let me give you a more simple example. Let's say you are in Montana and you're making widgets. Your widgets are very popular. Lots of people like to buy them, and you have this great business. But you're also polluting. And your pollution, because of the wind, doesn't blow into Montana. And so the people in Montana who are buying your widgets are not affected by it. It blows into another state. And those people don't buy your widgets. They don't benefit from the product that you're making in any way. And they can't influence your plant operations by choosing not to buy your product. And so the consequence is that there's this economic transaction going on between your plant and the people buying your widgets that has a negative impact on a third party that isn't actually part of the economic transaction and can't affect it. It's a market failure, and it's called a negative externality. And it's often a place where regulation is used, where the government comes in and they say, okay, your customers aren't going to stop buying your product because of this pollution, so we're going to require you to not pollute as much because the interests of this third party are important. Negative externalities can exist in protocol designs. A good example, I guess, is traffic amplification vulnerabilities. So like RTP, you can send a single packet, a single SIP packet, and get an RTP stream directed at a destination address of your choice, right? So you can send this one little packet and get a whole bunch of data to go to any destination on the internet that you want. It's supposed to come back to you, right? It's supposed to be a transaction between you and the SIP server. But you can target someone else as the destination, and as a consequence of that, that third party is negatively impacted, and they have no way within the context of this protocol to turn that stream off. They can't tell you to stop. Negative externalities in protocol design, I believe, we can have a positive impact by addressing them in the design, as opposed to simply pushing the way we address this down to the development level. And it goes back to this model. The protocol designers want to provide as much functionality to the vendors as they can, because that's who they serve. And the vendors want to provide as much functionality to the network operators as they can. But in fact, in some of these cases, if the protocol designers stop and decide to constrain their functionality a little bit, they will have a positive impact on the security of the actual software that gets deployed in the end. So the next question I want to talk about is what's going to happen in the future with wiretapping infrastructure, and I think this is probably the most interesting part of the talk. So illegal wiretapping used to be really easy. You used to be able to go out to a telco junction box with a couple of alligator clips and hook up and listen to somebody's phone call. You could get a frequency scanner and listen to people's cellular phone calls or their cordless calls really easily. Over time, it has been getting harder. Wireless systems are maybe more likely to be spread spectrum today. Cell phones have link layer encryption. A lot of the network traffic that's actually going over the physical infrastructure it uses protocols like DSL that are not as easy to decode. You can't just like hook up a little Radio Shack device and listen in. So it's becoming more difficult to do. But I don't know if we're going to achieve this ideal result where we have perfect end-to-end encryption. People don't tend to use end-to-end encryption systems that often because the actual process of authenticating them is too cumbersome. Where encryption seems to have really taken hold is when it's built into the link layer. And it's invisible to the user. Everybody uses encryption on their cell phones, but they're not aware of it. It's not something that they have to bother authenticating. So if you want to reduce the amount of illegal wiretapping that happens, doing work on making link layer protocols more likely to be encrypted is going to have a positive impact on that. There are still a bunch of link layer protocols that we use that do not have any encryption in them. And there are a lot of assumptions that people make about that. Something I didn't mention, I guess, about this lawful intercept system is that one of the things you can specify in the MIB when you're provisioning the wiretap is the VPN that you want to listen to. So there's this concept of a service provider VPN, and it always kind of rubbed me the wrong way because when I think VPN, I think encryption. And most people who are out there buying VPN technology think they're buying secure links. And the service provider industry has sort of sold this concept of service provider VPNs. And they're using the same terminology, but they're not using encryption. And when you push them about it, they say, well, you don't need to worry about that because the service provider network is not subject to surveillance. Well, in fact, it is. And in fact, you can specify the specific VPN you want to listen to in the interception request. So link layer encryption is actually a really good idea. The big question is, should we build this sort of infrastructure at all? Well, law enforcement likes to wiretap suspects, and I honestly think that we're not going to reach this point where it becomes technically impossible because I don't think everyone's going to adopt end-to-end encryption. So there's always going to be a place to hook up, and if there's a place to hook up, law enforcement is going to want to do it. They can either do it with temporary or permanent infrastructure. Those are the two choices. And the consensus view of the academic security research community is that the risks involved in creating permanent infrastructure are too great. That vulnerabilities like the ones I'm talking about in this talk will be used to take control of any permanent infrastructure that you build into the system. So use temporary infrastructure instead. Use portable protocol analyzers. I think that part of the reason for this view is that they also think that creating this permanent infrastructure makes wiretapping really inexpensive. It goes back to that economic analysis I was talking about. And so more wiretapping will occur if we have it. If we have this temporary infrastructure, it's more cumbersome, and so people choose not to do a wiretap when they otherwise would. So Susan Landau and Whitfield Diffie wrote a book called Privacy on the Line, which was published about 10 years ago that talks about this subject. And Susan actually reached out to me after I did this talk at Blackhat Federal. And I started talking to her about some of the things that I'm going to tell you in a minute about what I think is going to happen in the future. And she says, I really can't talk to you about this until you read my new book. When's it coming out? Well, it's coming out in March. So she's got a new book coming out in March, and if you're interested in this subject, I suggest you read it. I'm going to read it so that I can go back and talk to her about this stuff. But not having read it, I'm going to do something radical here, and I'm going to disagree with the consensus view of the security research community, and I'm going to provide you with a different perspective, for better or for worse. And hopefully it's food for thought. I think there are arguable advantages to having permanent infrastructure. Temporary devices don't have audit trails associated with them. Somebody goes to a storeroom and they check out this protocol analyzer, and then they go do a wiretap, and hopefully they only collected the data they were authorized to collect, and then a few weeks later they check it back in, right? If you have a permanent infrastructure, then you can create checks and balances and processes associated with access control. In fact, you have to, because you have to prevent unauthorized access. There are a couple different ways to build permanent infrastructure. One approach is the way that this Cisco architecture works, where you're actually doing minimization in the router itself. You're only collecting the data that you need to collect. The other way you can do this is to scoop up everything and sort it out later. And that's exactly what the Klein Declaration describes. The Klein Declaration is this. So this guy worked for AT&T, and he went to the EFF and told them about this room that existed in one of their switching centers where there was this fiber optic splitter, and all the network traffic was being shunted off to this room where it was being analyzed by the NSA, allegedly. And so in that case, we're not carefully selecting the data we want to look at. We're taking it all. So what kind of architecture do we want to have? I think that's really the discussion we need to be having. The key difference between the client and Cisco architectures is the presence of human checks and balances. And I think that you could build a wiretapping infrastructure that had good human checks and balances in it, that had good audit trails, and that required the right legal authorization to use the network. And if you simultaneously coupled that with efforts to improve link layer encryption, the consequence is that you would eliminate most illegal wiretapping. Most wiretapping would be legal. It's interesting because you'd have built into this wiretapping infrastructure a system that attempts to uphold people's constitutional rights. So it's a very different view than what the consensus view of the computer security research community thinks. But I present it for you for food for thought, and I'm going to be around all weekend to potentially discuss it if you're interested. So there's one other point I want to make, and that is that peer review is really important. This is how we build secure systems. Nobody in the world is building flawless software systems. And this conference for years has been a place where we come to discuss security vulnerabilities. And the way we do it is by looking through peer review, by looking at other people's technology and through a different perspective and seeing things that they haven't seen. So what Cisco did here is they published this architecture so that we can peer review it. And that's a great thing. And it's risky to do that because somebody is going to get up at a conference and they're going to talk about their technology, and nobody likes to be criticized. But the reality is that it's through this process of criticism that we actually achieve secure systems, and you all know that. So I think Cisco should be applauded for actually providing us with this architecture to review. And I think that there's a whole bunch of other lawful intercept technology out there that's actually in our telecommunications infrastructure that has not been subject to any peer review, that does not have any public architectural diagrams. There are all these different vendors that I mentioned that make mediation devices, for example, and who's looking at that stuff to see if it's vulnerable. Yesterday, Barnaby jackpotted an ATM on stage here, and people tend to have this assumption that ATMs would be pretty secure, right? The guys who would build stuff like that would really care about building something that was as solid as possible. But in fact, when you really look at it, it turns out there are weaknesses. Well, the same thing is true of just about any kind of technical system that we've deployed. And so until somebody actually does that kind of analysis and looks at it, we can't be assured of its security. So peer review is important, and that's my talk. Thank you very much for listening to me. I hope this was interesting. And again, I'm going to be around. Sir?
In the countries that require key escrow at present, do their lawful intercepts require that you be able to decrypt the data stream?
I lost my microphone. 1 second. Someone can correct me if I'm wrong, but I don't know of any country that currently requires key escrow. It was an idea that was promoted in the United States, but I don't know if you saw Moxie's talk earlier where he talked about choice. So key disclosure is sort of a different. So no, the wiretapping infrastructure isn't set up to enforce that key disclosure. In that key disclosure case, what happens is they come and they arrest you and they compel you to give them the key. And if you don't give them the key, you sit in a jail cell until you give it to them. So that's a very human approach as opposed to a technical approach. Sir.
The way a number of countries have gotten around that problem is they define laws that say you cannot do encryption of media.
That's right.
They don't have to worry about it.
Well, assuming they can enforce that rule, but if they start looking at your stuff and it's encrypted, then they can bust you for that. That's right.
They come back to the service provider,
Yeah.
not the end user necessarily.
I mean, I believe that no, I mean, I haven't. I know that Cisco did read my research, and I think that it takes a long time to change some of these systems. For example, the SNMP. So this guy at SNMP Research reached out to me, and they make their own custom SNMP stuff. And he said, I read your paper. Your recommendations for the SNMP protocol make a lot of sense, and we can implement them without a flag day. Do you have any customers that are demanding them? And I don't have customers that are saying we need to make these changes. I'm out talking about this because I'm trying to raise awareness about it to a certain extent. But until the phone companies actually want Cisco to make these changes, or want any other SNMP implementer to make these changes, they're not going to get made. It's their business relationship. And so all I can do is say, this is what I think. Hopefully the next time they design this, they'll consider my suggestions. But in terms of actually re-architecting the stuff in practice, it's for the vendors to decide. So let me get this question back here. Well, you'd have to establish, at least in the United States, and again, I'm not a lawyer, so ask one of the EFF people, but I think you have to establish standing, and so you've got to actually demonstrate that you were personally subject to unauthorized surveillance as a consequence of these vulnerabilities, and that's very difficult to establish. Well, the reality is that the court system won't consider your case unless you can demonstrate that you actually have meaningful harm. Go ahead. Oh, no, I don't know. I have no idea. I'd like to understand the purpose. Well, I do understand the purpose behind the lack of audit trails. They don't want the people who work for the phone company to know what they're doing. But I feel like there's another way to design it so that problem doesn't exist. And so I think that basically we can achieve an architecture that satisfies everyone's interests. But I don't know if we'll be able to have that dialogue or how we will have it, except coming here and talking about it and hoping that people are listening. Sir? So yeah, there's lots of thoughts in here that I didn't get out when I was speaking. So GNU Radio, for example, is this really cool project that lets you build software-defined radios. So a protocol analyzer, back in the day, you could go and get a phone and a couple of alligator clips, and you could go open a junction box and hook up to a phone line and listen to people's calls. It was that simple. But now, if they're doing VoIP over DSL, you have this whole protocol stack you have to parse, and so it's far more complicated. You can't just plug in a $15 device. There are companies that sell protocol analyzers that are used for that purpose, but they're very expensive, and so they're difficult to get your hands on. And so hopefully the inaccessibility of them has significantly reduced the amount of illegal wiretapping that happens. But if GNU Radio can do that same kind of protocol analysis, then it could peel apart the ADSL layer and peel apart the VoIP layer, and so you could then again get to the point where you take this laptop running open source software to a junction box and plug it in, and you can listen to people's stuff. And so that's a technical direction I'm just pointing out where we sort of, things got really hard because the protocols got complicated and the systems required to parse them are expensive, but over time it may get cheap again to parse those protocols. And so again, it's an argument for why it makes sense to do link layer encryption, because ultimately, if you're not doing link layer encryption, somebody can get access to the infrastructure and listen to the calls. So, any other questions, or should I shut it down? Thanks, everybody.